The reality you see around you, that solid, predictable, objective one, might be just an illusion. And this isn't said by an eccentric philosopher, but by the most solid and verified scientific theory humanity has ever conceived, quantum mechanics. And if you think this is just a peculiarity concerning invisible particles, prepare to change your mind. A new, incredible experiment has just confirmed one of its most absurd predictions, demonstrating that movement can arise from nothing. Today, we will travel to the borders of our understanding, where physics clashes with reality and forces us to ask ourselves, is what we see all that exists? This is a journey that requires an open mind. To support this exploration free from dogmas and prejudices, consider subscribing to the channel. Click on the button below. And now, fasten the seatbelts of your mind. Quantum mechanics has radically changed our vision of reality, and that's why physicists talk about it so much. It's difficult to understand how deeply it has overturned our understanding of the world. The first reason for bewilderment is that quantum mechanics states that small particles can do things we don't see everyday objects do. For quantum physics, everything is described by a so-called wave function, which is calculated by solving the famous Schrödinger equation. The problem is that this equation is linear. This means that if a particle can go one way and the same particle can go another way, then it can also be in a superposition of states. That is, it can go simultaneously one way plus the other. We often say that the particle is in two places at the same time. But what does this really mean? We have the mathematics to describe it, but we lack the words. Particles don't behave at all as we would expect. If you take a single particle and put it in the center of a box, its wave function expands, it spreads out. It doesn't stay still there. A particle coming from a distant supernova might have traveled for half the universe, with its wave function expanded for millions of light years in diameter. Yet when we measure it, it suddenly appears in a single point in our detector. And here comes into play an even stranger concept: zero-point energy. It's a purely quantum phenomenon. A classical particle, if put in a well, can simply stop at the bottom at zero energy. But a quantum particle is also a wave, and its wavelength must fit into the space in which it is confined. This means it can never stop oscillating, and if it oscillates, it has energy. There is therefore a minimum inevitable energy that always exists, even at the lowest possible temperature, even in absolute vacuum. It's zero-point energy. But if there is energy, there should also be movement. A zero-point movement. Things should move randomly, without an apparent cause, as if by magic. It seems absurd, but this is what mathematics predicts. Well, a new experiment has demonstrated that everything is true. Researchers wanted to verify if atoms inside a molecule move due to this zero-point energy, even when the molecule is in its lowest possible energy state. To do this, they used a brilliant technique. They took a large molecule and bombarded it with a very powerful laser, stripping away all its electrons. Without electrons to act as glue, the atomic nuclei, all positively charged, violently repelled each other, and the molecule literally exploded. By precisely measuring the momentum of each individual nucleus after the explosion, they were able to calculate backwards how much they were moving before, due to zero-point motion alone. The result was unequivocal. Zero-point motion is real. Once again, quantum mechanics has won its challenge against common sense. This confirmation brings us to an even deeper level of strangeness: the lack of defined properties. We think that objects have precise properties, regardless of whether we look at them or not. A ball is in the garden, even if we're not checking it. But in quantum physics, it's not like that. A particle can be in multiple places simultaneously until we measure it, and only at that moment does it decide where to be. But what does it mean for a particle not to be really anywhere before being measured? The idea that properties don't exist before a measurement is so counterintuitive that Erwin Schrödinger devised his famous thought experiment of the cat. Imagine an atom that can be both decayed and not decayed. This atom is connected to a mechanism that, if the atom decays, releases poison and kills a cat closed in a box. If you believe in the mathematics of quantum physics, then before opening the box and measuring the state of the atom is both decayed and not decayed. The poison is both released and not released, and the cat is simultaneously both alive and dead. Obviously, we never observe cats half alive and half dead. But why? Some physicists say that the environment itself constantly measures the cat. Others, following the many worlds interpretation, suggest that the universe splits in two, one in which the cat is alive and one in which it's dead. But are these solutions really less strange than a cat alive and dead? Quantum physics doesn't give us easy answers, but opens us to dizzying questions. We started from a new experiment that confirms a strange property of the subatomic world, motion from nothing, and we arrived at questioning the existence of an objective and shareable reality. Quantum physics teaches us a deep and humble lesson. The world is much stranger and more mysterious than our intuition lets us believe. It doesn't offer us certainties, but gives us an infinite sense of wonder, showing us that reality could be a fabric of infinite potentialities, a dream from which perhaps, by measuring it, we only partially wake up. Thank you for having traveled with us to the borders of reality. If this video has fascinated you and pushed you to reflect, subscribe to the channel so you don't miss the next explorations. Your support is fundamental. Thanks again, and see you next time.